So continuing on, what I want to do is go over a number of more different examples of polar coordinates and integrating in polar coordinates so that you feel comfortable and confident doing this. And we'll also touch on more general coordinate systems as well, because it is important for you to know how to get the area element from the Jacobian matrix and use that as well. But one of the main tools that you want to first become comfortable with is doing it in polar coordinates. So again, what we've seen is that the double integral in Cartesian coordinates of a function is going to be the same thing as the double integral over the same region R. The bounds are going to change. The description of the region is going to change, but the region stays the same. So it's the double integral over R of the same function, but with the polar coordinate transformation plugged in for x and plugged in for y. And then what also changes is the area element, or the dA, because the boxes in the Riemann sums in polar coordinates are going to be of a different shape, right, than the boxes in Cartesian coordinates, which are standard rectangular boxes. The boxes in polar coordinates are circular segments, right, and this is evidence if we scroll down a little bit here and look at this picture again of polar coordinates, where we see very clearly that right, if you do Riemann sums for in integral and polar coordinates, the boxes for the Riemann sums change shape to these circular segments right here. So if you're, say, integrating over a region, these circular segments are getting smaller and smaller and smaller, and the area of each one of these boxes has a different form, and this is why this r d theta appears. And we saw in a little earlier that the reason for this is directly due to this Jacobian matrix. But you really can kind of see this if you look at the example that I showed in the coordinate systems lecture, which is of this image mapping. You take this image mapping right here, this is what it looks like in Cartesian coordinates, and then you map it into polar coordinates for various values of the radius and the angle. The image looks like this, right? And you're seeing that the area is being distorted proportional to r. So the area of, say, the eye of this cat right here, right, is being distorted a little bit less than the area here, which is further out along on the radius value. This area right here gets distorted a lot more. So this really kind of provides good, I think, strong evidence for why, right, you need to alter this. Another cool thing that you see here is that if you, say, plot out and you look at, we'll zoom in a little bit here, one of the whiskers of the cat, see this one right here, it's kind of neat to see that this curve right here in Cartesian coordinates then changes to this curve right here in polar coordinates, which is really neat. But so let's kind of move into one example, or another big example that'll help us along. And this example is going to be related to temperature distribution. Specifically, let's say we have a circular plate, and we have that on this plate, right, the temperature is distributed in a way that the middle of the plate is 2 degrees Fahrenheit. So suppose that we have a circular plate of radius, we'll just say radius 1, And let's make this a little bit more, a little bit different. So we'll say a semicircular plate. So a semicircular plate of radius 1 is the equation x squared plus y squared is less than or equal to 1, and y is greater than or equal to 0. Okay, that's half a circle. Such that the temperature is given by, and we'll say at each point x, y, it's given by a function of x and y, specifically, let's say the function t of x, y is equal to 2 over 1 plus x squared plus y squared to the 4th. So if we look at this this function, right, this plate right here, this plate has a circular domain and only half of a circle. If you look at the level curves of this function, the value of the function at the origin is just going to be 2. The value of the function at the boundary, where x squared plus y squared is equal to 1, this is a circular plate of radius 1. And I'll actually color this one red, because that's the maximum value of the function. The value of this function at the boundary is given by 2 over 2, or 1. That's 1 degree. We'll use just degrees Fahrenheit. 1 degree Fahrenheit on the boundary, 2 degrees Fahrenheit the origin right here, and then as we move throughout the plate, the level curves are circles, so the temperature of the function is gradually decreasing from 2 to 1 as we move throughout this plate right here. Oops. There we go, like that. So this is a nice picture, kind of corresponding to exactly what we're dealing with in this problem. So now suppose that we want to do some sort of integral of this function. Just for example, let's say we're interested in the average value of temperature over this plate right here. Now, it's not correct just to average the maximum and minimum values, right? This is not the correct way of getting the average. We know from before that the average value of a function, we went over this a couple lectures ago, average value of a function f of 2 variables, in this case, might as well use t here. This is going to be equal to the double integral, or accumulation, of the function over the region, divided by the total size of that region, the area of that region. And this is something that we actually don't need much help in computing, because we already computed in 2 separate ways the area of a circle. Right? We know that the area of a circle, because R is a circle, And I've done this calculation now for you in Cartesian coordinates and in polar coordinates, so you should really be familiar with where pi r squared is coming from. But so this is r is a semicircle from the problem. So this is going to be pi times 1 squared over 2, or pi over 2. And so the only other value that we need now to get the average value of temperature on this region is the accumulation of the function itself on the region, or the double integral of the temperature function over the region R. This is going to be the double integral of function 2 over 1 plus x squared plus y squared. Oops, and I just realized that my example here should be to the power 2, not to the power 4. You can still do to the power 4, the integration just works out a little bit more complicated. So we're going to stick to the power 2 here. Sorry about that. Anyway, so the easiest way of integrating this function is going through and using polar coordinates. So this is going to be double integral over 2 over 1 plus x squared plus y squared is the same thing as r squared. So this is r squared to the power 2. And then remember, dy dx in polar coordinates has to become r dr d theta. And you could try and write down the bounds in Cartesian coordinates. I've done that for a number of different circular integrals before. Just to kind of show you, I guess I'll write them down right here. The bounds in Cartesian coordinates would be from -1 to 1, and then from 0 to the square root of 1 minus x squared. These are the bounds for this region right here in Cartesian coordinates, because we're going from -1 here to 1, and then 0 up to the curve y equals the square root of 1 minus x squared. So these are the correct bounds of Cartesian coordinates, but it's much easier in polar coordinates, both to do this integral and also to re-express the bounds. Bounds here are going to be from 0 to pi, because this is 0, an angle of 0 to 180 here, to describe this entire region, which is 0 to pi. And then the radius is going from 0 to 1. So you see it's much easier. The integration process also becomes much easier, because you see here we have 2r dr here, and we have an r squared here. So if we do a u substitution of u is equal to r squared, then du will be equal to 2r dr. And this will become the integral from 0 to pi still, and the integral of from u at 0, which is 0 squared, or 0, to an upper bound of 1 squared, which is u at 1, which is 1. So it'll be then 2 over 1 plus u squared du. And from your Calculus 2 class, you'll recognize this immediately as related to and also this 2 here goes away because of the integration by substitution here. You have 2r dr, which is the same thing as du. But you'll immediately recognize this integral as the arctangent, the antiderivative 1 over 1 plus u squared with respect to u is the arctangent function. And this can be proved using trigonometric integration, trigonometric substitution, but this is typically done in a Calc 2 class, so we're just going to take this as known. I can go over the details with that if you like, but this is arctangent of u now evaluated from 1 to 0. Which is just going to be pi times arctangent of 1 minus arctangent of 0. Because you have to do the integral of 1 d theta here as well, which is where this pi is coming from. But anyway, so we evaluate the arctangent of 1. This is equal to pi over 4. Arctangent of 0 is just 0. And so our final answer becomes, for this value, becomes pi squared over 4. And remember what we're evaluating here in this integral. We're evaluating the double integral of the function over our temperature function dA. So this value that we've calculated is just the accumulation of temperature in this region. So this value is meaning, and because the function is positive, you can think of it as the net volume under the graph of the temperature function. But so kind of pairing this now together with our area, we have that the average value of temperature from our average value formula from before, this is now equal to pi squared over 4 divided by the area, which is pi over 2, which simplifies down to the value pi over 2 for our answer. And this is approximately equal to 1.570796. Right, so the average temperature is approximately 1.57 degrees Fahrenheit in the region. Alright, which is definitely not an average value of the maximum and minimum values of temperature. It's close, but it's a little bit different. And for many different functions, you can probably clearly see that this might be much, much different. But this is kind of a neat process. So this gives us a way of evaluating averages of any general function. And even if you don't have the actual function, if you just have data, say, you can approximate the average value of a function using a Riemann sum approximation. Right, which is why I think it's important, and I've included a number of those in the web work, so you can kind of get experience with doing that, because that's how you take real data and you approximate a volume, or you approximate, say, the average value or of accumulation of a given function using real world data. So now we'll consider a new problem, which is solving for a double integral over a region that is very complicated and is going to involve solving for the specific coordinate system coming from the domain itself, similar to how we did polar coordinates. I'm going to capitalize on symmetries. So for this example, what we'll say is that we're going to look for just the area of the region bounded by the curves y equals 1/5 x, y equals 3x, y equals 2 over x squared, and y equals 9 over x squared. And we can get a quick visualization of this. If we plot out what these curves look like, the curve y equals 3x is a straight line in the yx plane. of slope 5. The curve y equals 1/5 x is a straight line of slope 1/5. And the curve y equals 2 over x squared and y equals 9 over x squared are going to be curves that look like this, with an asymptote at x equals 0 and an asymptote at y equals 0. Same thing for the curve y equals 9x squared, which is going to be shifted up a little bit. And the region that we're going to look for the area of is this region right here. Now you can already clearly see that finding this area, the area of this region R, through a normal Cartesian coordinate double integral is going to be miserable. Very, very, very hard, because it's going to involve solving for the intersection points. In this case, we have 4 intersection points. And then we're going to have piecewise functions for our upper bounds and our lower bounds. Because as we go from the leftmost point in the domain to the rightmost point in the domain, the upper bound is changing here and the lower bound is changing here. So this is just going to be a very, very long process. We can go through and do this, but using new coordinate system that's directly defined based on this region is going to be much simpler. And this figure right here just kind of is a direct plot from Desmos of this these 4 boundary curves, and I've even shaded this region right here. So this region right here is the region between the curves 1/5 x and 3x, and this region right here is the region between the curves 2 over x squared and 9 over x squared. And the dark gray region right here is the intersection region that we're looking for the area of. And you can very clearly see that it's not going to be easy to do this in Cartesian coordinates. The correct way of doing it is by introducing a new coordinate system that is essentially symmetric and nice with respect to this region. So the question becomes, how do we do this? Well, you can notice that there's a way of rewriting these boundary curves. These boundary curves as y over x is equal to 1/5, and y over x is equal to 3 for this curve. X squared times y is equal to 2, and x squared times y is equal to 9. We have exactly what our new coordinate system should be. Specifically, if I introduce new coordinate u to be equal to x squared times y, and new coordinate v to be equal to y over x, okay? This is the correct coordinate system to use for this domain, for integrating over this domain, because this lower curve right here is given by v is equal to 1/5. This upper boundary right here is given by v is equal to 3. This lower curve right here is given by u is equal to 2. And this upper curve right here is given by u is equal to 9. And so in UV space, if you were to visualize this in UV space, we have that this region is just a rectangle in UV space, and the integral of a rectangle is always going to be easier to evaluate. The catch here is that we need to find the Jacobian matrix of this transformation. The Jacobian matrix, you'll recall, is the matrix of partial derivatives of x and y with respect to u and v, or the matrix dx du dx dv dy du dy dv. And finding this is a little bit of a procedure because we don't have x and y as functions of u and v. We have the opposite. We have u and v as functions of x and y. So there are a couple different ways of doing this. One of them is a really nice result using linear algebra, but I'm not going to use that method because several of you may have had linear algebra, but many of you may have not. So what we're going to do is just kind of look at this and say, well, okay, let's solve directly for x and solve directly for y and go through and do it directly. And this is not too difficult. Because if you notice, with taking our equations, defining the reverse coordinate transformation, if we're going to solve for x, we can do that in a relatively straightforward manner by dividing u by v. If we divide u by v, u divided by v is just going to be x squared times y divided by y over x, which will be x cubed. So x is equal to u over v to the 1/3, or u to the 1/3 times v to the negative 1/3. And likewise, if we multiply these two things together, specifically u, and we actually multiply it by v squared, we're going to end up getting that this is x squared times y squared over x squared. In the first case, the y cancels out. In this case, the x squared here is going to cancel out, and we'll get that u times v squared is equal to y cubed. So y is equal to the cube root of u times v squared, or u to the 1/3 times v to the 2/3. And there you have it. So this is our x as a function of u and v, and this is our y as a function of u and v. And this allows us to go through and compute the Jacobian matrix and the Jacobian determinant of this coordinate transformation so that we can do our integral. So what we need to do now is go through and evaluate our Jacobian matrix, which luckily is relatively straightforward to do, that we have x and y. And this is going to be exactly given by the x partial derivative with respect to u in this first component, which is 1/3 u to the 2/3, to the negative 2/3. This is the partial derivative of this with respect to u times v to the negative 1/3. And the x partial derivative with respect to v is going to be negative 1/3 times u to the 1/3, v to the negative 2/3, or negative 4/3. This is just the power rule applied to each one of these. The y partial derivative with respect to u is going to be 1/3 u to the negative 2/3 times v to the 2/3. And the y partial derivative with respect to v is going to be 2/3 u to the 1/3 times v to the negative 1/3. And so in our integration, the determinant of this Jacobian matrix is going to be the diagonal, so this times this minus this times this, which is going to give us 2/9. 1/3 times 2/3 is 2/9. U to the negative 2/3 times u to the 1/3 gives us u to the negative 1/3. V to the negative 1/3 times v to the negative 1/3 gives us v to the negative 2/3. And then lastly, this is going to be subtracting this times this, which will be -1/9. Then u to the -2/3 times u to the 1/3 is going to give us u to the -1/3. And v to the 2/3 times v to the -4/3 is going to give us v to the -2/3. So this simplifies nicely to 3/9 u to the -1/3 v to the -2/3. This is our Jacobian determinant term. It's positive because u and v are positive, so we don't have to worry about the absolute value when we integrate. And finally, we have an expression for our area. The area of the region R is going to be the double integral over R of 1 dA, or dy dx, which in our uv coordinates is going to be the absolute value of the determinant of the Jacobian matrix, dv du. And this is the same thing as we computed, as the double integral over R of 3/9 u to the -1/3 v to the -2/3 dv du. And what's nice now is that the bounds of integration are very easily found from this picture. We drew the picture. This is going from u from 2 to 9 and v from 1/5 to 3, which is a rectangular domain in uv space, and that means that the area of R, of our region, is given by the double integral from 2 to 9 for the variable u, and 1/5 to 3 for the variable v. And this is the double integral of 3/9 u to the -1/3 v to the -2/3 dv du. And this is a relatively straightforward integral to go through and evaluate. First off, the constant will come out. This will be 3/9. And not only that, we have a function of u here and a function of v here. So when we go through and integrate, this is going to become the integral from 2 to 9. U doesn't depend on v, so that comes out of the integral. We do our iterated integral first. This inner iterated integral simplifies very nicely to just being 3 times v to the 1/3 so this is 3 times v to the 1/3. This is evaluated from 3 to 1/5. So this is going to be equal to, on the outside, 9 over 9, because the 3 comes out, times 3 to the 1/3 minus 1/5 to the 1/3, or 1 over 5 to the 1/3. And we have to multiply this by the integral of u to the -1/3 from 2 to 9, which is just going to be equal to 3/2 u to the 2/3 from 9 to 2. And so our final answer then will be 3/2 times 3 to the 1/3 minus 1/5 to the 1/3 times 9 to the 2/3 minus 2 to the 2/3. Which is approximately equal to 3.2 or 3.52326. This value is approximately equal to 3.52326. This is units squared. So if the distance along x and y that you're measuring is meters, then this would be 3.52326 meters squared. If the distance isn't any other length, it's whatever that unit is. But this is what this value is. This is an exact value for the area of this relatively complicated non-rectangular region R. Right, so this shows how to correctly compute areas, even if the area is non-rectangular region. And it shows how general coordinate systems are very useful. So the final example we'll consider actually is not an engineering example, but it's actually an application to probability. And in probability, there's what's called a probability distribution that many of you will actually know as the bell curve or the normal distribution. And simply put, what this describes is what's called a random variable. That random variable could be a number of different things. Say, for instance, grades in a class or test scores, average height, average any property that you can think of. It doesn't always follow the normal distribution, but very, very, very frequently you have that real physical measurements will follow what's called a normal distribution or a bell curve, and that's essentially a curve that is centered around some mean. You also have this parameter called the standard deviation. Or standard difference or distance from the mean. You can think of it as the average distance from the mean. And the bell curve has the following shape. It comes up, like this, and then comes down. And it's symmetric about the mean. So it describes, whenever you have some measurement or some phenomena that's centered about a mean, and very quickly the probability of occurrence gets smaller and smaller and smaller as you move away from that mean value. So here mu is the mean, and sigma is called the standard deviation. And in a general probability and statistics class, you'll learn about what are called probability density functions, and that for any given random variable, you can describe that random variable using its probability density function. So the probability density function for the normal distribution is the following function. It's 1 over sigma times the square root of 2 pi times e to the negative 1/2 x minus mu over sigma squared. This curve, or a curve with this shape, gives us exactly this bell curve. This is the exact function that gives you the bell curve. there are many reasons for this, many ways of kind of describing this. It's actually a really interesting theorem that you'll get to in probability and statistics called the central limit theorem, which in some sense roughly states that the average of multiple samples, right, of a given random variable will eventually converge to this normal distribution, which is a very, very powerful idea, and it's applied all of the time in what's called hypothesis testing. But the main thing for us is to look at a relatively one of the most important things here in prob and stats, which is how to determine what's called the normalization constant. So this constant in front of the exponential, I'm circling it right here, this is called the normalization constant. And essentially what this does is it guarantees that the area under this curve, or the area under the probability density function, so this area right here, this normalization constant guarantees that this area is equal to 1. Which is extremely important in probability and statistics. For any probability density function, this normalization constant has to be chosen so that the area under the probability density function, or the integral from negative infinity to infinity of the probability density function, so this is chosen, the normalization constant has to be chosen so that area under the PDF is 1. This improper integral from negative infinity to infinity of the probability density function has to be equal to 1. And you look at this, you see 1 over sigma times the square root of 2 pi. And you could ask, where is this coming from? And it turns out that we can go through and directly do this, right, by considering actually a multiple integral. So we kind of use a little bit of a trick, and we use multivariable integration, and we also use polar coordinates in order to find this. The reason that this has to be true is because in some sense this is mathematically equivalent to saying that all probabilities mathematically sum to 1. But the sum of every single outcome, every single possibility, has to be equal to 1. Now, a deeper discussion of this is definitely had in a probability and statistics course, but for us, we're just going to take the fact that we want this integral to be 1 and go through and see exactly how to ensure this, how to figure this out. And we're going to do this by considering the following. We'll go through and consider just for what's called the standard normal distribution. So the standard normal distribution is a normal distribution with mu equal to 0, so a mean of 0, centered at 0, and a standard deviation of 1. So it's a bell curve that's centered at 0 and has a standard deviation of 1. It still has that bell shape though. in this case, the function that we're dealing with, we want to normalize or figure out what the constant, we'll call it c, should be, such that c times e to the negative x squared over 2, the integral of this function, is 1. The improper integral from negative infinity to infinity. So the integral of this function has to be equal to 1. So this is the same thing as c times the integral from negative infinity to infinity of e to the negative x squared over 2 being equal to 1. And just for simplification, if we'll call this I, because this is the integral that we want to figure out now. But this normalization constant c should be equal to 1 over I to satisfy the equation c times I is equal to 1. So if we can figure out the integral of this function, then we have our normalization constant. So the trick here is that we need to figure out what I is. So go through and calculate I, which is the integral from negative infinity to infinity of e to the negative x squared over 2 dx. So the question is how to determine this. And what you'll see is that this is a relatively difficult problem. It's difficult because of the fact that we've talked about before, the function e to the negative x squared over 2, right, and specifically the antiderivative of the function e to the negative x squared over 2 does not exist in closed form. Meaning that we can't express it in closed form or in terms of nice functions. So doing this integral in a standard manner is by finding the antiderivative of this function and then using our results on improper integrals to evaluate the limit is not going to fly. We're not going to be able to compute that. So we need to look for a different method of figuring out what this integral is. And it turns out that this is directly possible to do using a multivariable calculus in polar coordinates in a very, very clever manner. So instead of solving for I, we consider solving for I squared, or I times I. Because if I can solve for I squared, then whatever result I get for I squared, I can take the square root of that result and exactly have what I is going to be. So I squared is equal to I times I, where I is the integral from negative infinity to infinity of e to the negative x squared over 2 times the integral from negative infinity to infinity. And I'm going to use a different variable for this second integral because it's a separate integral. You can use any variable you want because it's a dummy variable. So I squared is just the product of two single variable integrals. And what's very neat here is that one of our properties for the integral is that if you have two separate integrals, both being multiplied, or both of different variables, right? Two separate single variable integrals being multiplied together, this is identical to the double integral of the product of these two functions. Which can be rewritten as the double integral e to the negative x squared over 2 times e to the negative y squared over 2 is negative 1/2 x squared plus y squared. And we also want to remember that this integral, right? These bounds mean: negative infinity to positive infinity in x, and negative infinity to positive infinity in y. Right? These bounds are describing the entire real plane. So all of this, every single point in the real plane, two-dimensional real plane. So this is an integral that looks very, very nice. Hopefully, if you look at it, you think about what this is going to look like in polar coordinates. It's a double integral that hopefully will be a little bit nicer in polar coordinates because it has a lot of radial symmetry. It has symmetry around, there's like no dependence on theta here at all. You'll see that directly, that x squared plus y squared in polar coordinates is r squared. This will be e to the negative 1/2 times r squared. And remember that in polar coordinates, dA is equal to r dr d theta. This is very important. So it's r dr d theta. This dx dy becomes r dr d theta, which is an integral that we can evaluate. The inner integral here is a u substitution integral, and it's a relatively straightforward u substitution at that. We also want to consider the bounds. The bounds are going to be, as follows. It'll be for theta from 0 to 2 pi, because we want to describe every single point going around the origin. And then our r bounds, to describe every single point in two-dimensional space, we have to go from 0 in r all the way out to positive infinity. That will allow us to describe every single point in two-dimensional space. So even the bounds become nicer in polar coordinates. This is going to be the integral from 0 to 2 pi. And now we can go through and actually evaluate this using improper integrals. The inner integral here is an improper integral. So it's going to be the limit as b goes to infinity of the integral from 0 to b of r times e to the negative r squared over 2 dr d theta. So remember from a previous calc course, you should remember improper integrals, and that's how we evaluate that inner integral using a limit. And we can simplify this a little bit by using u substitution. So we do a u substitution of u is equal to r squared over 2. Then du will be equal to r dr. This will be the integral from 0 to 2 pi of the limit as b goes to infinity of the integral from 0, and then so if when r is 0, u is 0. When r is b, u is b squared over 2. So it's the limit as b goes to infinity of the integral from 0 to b squared over 2 of e to the negative u du. So this is equal to the integral from 0 to 2 pi of the limit as b goes to infinity. This antiderivative is going to be negative e to the negative u from b squared over 2 to 0. And when you plug in the bounds, this becomes the integral from 0 to 2 pi of the limit as b goes to infinity of be e to the 0, which is 1, minus e to the b squared over negative b squared over 2. The limit of which is equal to 1. The limit of 1 is 1, and the limit of e to the negative b squared over 2 is equal to 0. So this is just going to be equal to the integral from 0 to 2 pi of 1 minus 0, or the integral from 0 to 2 pi of 1, which is equal to 2 pi. So that's it. That's the value of that integral, which, remember, this double integral is the same thing, and we're going all the way back to the very beginning, as I squared. So what we've shown is that I squared is equal to 2 pi, which means that I, the integral that we're looking for, the integral from negative infinity to infinity of e to the negative x squared over 2, is equal to the square root of 2 pi and our normalization constant, c, for the probability function, the probability density function, is going to be 1 over I, or 1 over the square root of 2 pi, which is exactly what we had when we wrote down the general standard normal distribution. Now remember, this calculation is for the normalization constant for a standard normal distribution. For the general normal distribution with a non-zero or non-1 value of the standard deviation sigma, you're going to have a little bit of a change here. You'll have a sigma that appears as we wrote down before. But the idea is that that I'm trying to convey with this example is that multivariable integration is actually very, very useful, even when applied sometimes for certain scenarios to single variable integrals. And polar coordinates are essential to going through and figuring out very often what a double integral is for many different types of applications. And the point of the examples that I've shown in this lecture are just to kind of emphasize that. But I guess the main point of this last example is to show that sometimes the double integral can be used to actually evaluate a single variable integral in special circumstances, and B, that improper integrals can also be combined, right, in a very efficient manner to do this. And this is what we've done in this last example. But this will wrap it up for the lecture today. Thank you very much for tuning in. I hope you had a great day and are excited for the next lecture, which will cover more applications of double integration.